This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for today's Satellite Book Club Seminar Series, session number 76. I hope everybody had a good Thanksgiving. Happy meteorological winter. A little less of a winter topic today, the August 10th, 2020 Derecho, Hints of Evolving Threats in Satellite Data. Our presenter, Borchardt, meteorologist at the National Weather Service Forecast Office in Chicago, Illinois. We're glad to have Sharon Sullivan, aviation meteorologist at the Center Weather Service Unit in Albuquerque, New Mexico, facilitating. Just a few reminders before we get started that the session is being recorded. There will be an opportunity for Q&A after the presentation. Please post your questions in the chat room, even if you'd like to go on microphone. That will help us field them. We are particularly looking for questions and comments from our field offices and regional headquarters. So don't be shy, and we'd love to hear your contributions and your thoughts on this presentation. We're always looking for future presenters, so if you have an application you'd like to share with your colleagues, please get in touch with us. And if you're looking for training materials, Brian Mata at the Office of the Chief Learning Officer can help you with that. I'd like to thank the Tower S team, particularly Kashad Bowman, Lee Byerly, the Office of the Chief Learning Officer, the GOZAR and JPSS programs for their support of the Satellite Book Club, and of course our presenter and facilitator for being with us today for what should be an excellent presentation. Without further ado, I'd like to introduce Brett Borchardt, a meteorologist with the Forecast Office at Romeoville, Illinois, known as NWS Chicago, with warning responsibilities for part of northern Illinois, northwestern Indiana, and Lake Michigan. Having lived in the Great Lakes for the majority of his professional and personal life, Brett is familiar with summertime mesoscale convective systems that often present operational forecasting and warning challenges. He graduated from the University of Oklahoma in 2016 with a bachelor's degree and previously served as a meteorologist at the forecast offices in Marquette and Grand Rapids, Michigan. So Brett, looking forward to your presentation. Thanks for being with us.
Hey, thanks for the introduction and thanks for having me and for the invitation to speak to the Satellite Book Club. This is a fascinating topic, one that I am definitely passionate about, having lived through it and warned through this event. And you mentioned the warm weather across the central United States. It's currently 55 degrees outside in Chicago on December 2nd, go figure. So just incredible weather, thankfully not expecting to deal with anything like this storm anytime soon. And frankly, I'd be fine if we don't have to deal with it ever again. But yeah, why don't we talk about a unique topic here, a little bit different than the time of year, talking about a derecho that impacted the so-called Corn Belt of the United States in 2020. Of course, got to start off with a satellite image here. This is, I believe it's 1 minute data with GLM data overlaid, just showing really just the incredible storm as it went across Illinois. I want to talk about some fast facts first here, just about this derecho. Really just a once in a generation event, once in a career event potentially. Well, damaging winds covering an area greater than 90,000 square miles, just an obnoxiously huge area. It impacted more than 20 million people and more than 1 million homes lost power. And that's homes, that's not necessarily people. So you have multiple people who live in homes. So you're talking about millions of people without power. In the middle of August, in the Corn Belt where the corn sweats, it's really humid. So just a really high impact power outage across part of the area. And the peak estimated winds were really estimated at 140 miles an hour in the hardest hit area, and a much larger area where winds were estimated to be over 100 miles an hour, the peak winds, which is incredible for any convective system, let alone one that was as persistent as this derecho. And there were at least 27 tornadoes produced by the storm. And I say at least because we suspect there were many more. However, with the 100 mile an hour winds behind the leading edge, sometimes it's impossible to discriminate tornado paths, and in some degree, it may not even matter because 100 mile an hour winds are 100 mile an hour winds. But just numerous tornadoes, many of those in our forecast area. And this was actually our second biggest tornado event on record in our forecast area in Chicago, second to actually another derecho, interestingly enough. And this was the costliest thunderstorm event in US history, a big headline there, with $11.5 billion with a B, $billion in damage a lot of that to agricultural crops and farms across Iowa and western Illinois. Now, unfortunately, there were 4 fatalities from this thunderstorm and numerous injuries. And I'll be upfront, this storm was not well forecasted. We did not anticipate this storm coming through our area. We had lead time of less than a day, and even as the storm was occurring, the evolution of the derecho was still challenging to us. We had to adjust our strategies on the fly, even as we were warning, which sometimes we have to do that. That's okay, and we can adapt well. But this was an extremely challenging forecast event. It seems like a lot of high-end derechos present forecasting challenges. I think back to the 2012 derecho that went all the way to the Atlantic coast that actually started in the Chicago area, another challenging forecast. So derechos are just a fantastic opportunity for learning and additional research. Now, the damage from this derecho was just incredible from a meteorological standpoint and really terrible from a human suffering standpoint. Just a few pictures here. 200-foot radio tower north of Marion, Iowa was downed. The Quad Cities forecast office had estimated at least 130 mile-an-hour winds to bring that down. The bottom left picture there is what used to be a hog confinement building east of Marshalltown, Iowa. And I believe there was actually a measured wind gust well over 100 miles an hour in Marshalltown. And these pictures aren't cherry picked. The damage was just ubiquitous across Iowa and western Illinois like this. Just incredible wind damage. And I have a video here. This is from Cedar Rapids, Iowa, off of YouTube. And turn the sound off, but just incredible winds bringing down trees. It's estimated that Cedar Rapids lost about 70% of their tree canopy. And that's just, I can't fathom that. 70% of all trees just gone in one storm. And the damaging winds lasted a really long time. This video, I started it at about 14 minutes in. If I go all the way to the end, 28 minutes in, it's still blowing. If anything at all, the winds are actually stronger 28 minutes into the storm. And in some of the hardest hit areas, the damaging winds lasted longer than 45 or even 60 minutes, which is, that's just ridiculous. And if we were to compare the view here, I know it's a little obscured by the rain, but you can see some, branches sticking up at the ends of the street there. Just look at the view. It's just a complete change in the character of this neighborhood from this one single storm. Again, a once in a generation storm, hopefully just once in a generation, just incredible storm across the Corn Belt. And the damage was visible from space, especially the agricultural damage. This is taken from the NASA Terra satellites, taken roughly 2 weeks apart from July 28th to August 11, 2020. And it's really obvious to see the footprint of corn damage. Just to see what this looks like on the ground, this is a picture taken just northwest of Des Moines. Just flattened corn for miles and miles and miles, thousands and thousands of acres. And it's not like this corn was able to just bounce back up after a week and farmers were able to harvest it. No, this corn was destroyed, gone. It's a total loss for these farmers. And this is right through the Corn Belt, right through I-80, just destroyed corn. And incredibly impressive to see this from satellite, again, from a single storm. So let's talk about the damage produced by this tornado a little bit more from a meteorological scale. This was a map that was produced by Scott Lincoln. He's the senior service hydrologist in the forecast office, Chicago forecast office. And he worked with all the impacted offices from the storm to generate this map of the estimated wind speeds, which are shaded. And we also have tornado tracks on there as well as the lines, at least the tornadoes that we know of. And this is a pretty remarkable map. For one, just to see the difference in the characteristic of the damage as the derecho progressed from Iowa into Illinois. Just add some annotations on here. When the storm was going through Iowa, you had a roughly 3 to 4 county wide area of high-end damaging winds, like I mentioned, lasting as long as 30 or more minutes. And you see those swaths there of 100+ mile-an-hour winds, just large swaths, multi-county swaths of these high-end winds. If you compare that to northeastern Illinois, we had the damaging wind zone broaden. Notice the blue shading there broadened to be about half the state into Indiana there. And we also saw the highest winds start to be co-located with these fingers of damage, or confined to the fingers of damage, in which there were numerous tornadoes. And this is not a transition that we expected in our forecast office. I was actually on duties for issuing warnings for this event, and I thought this was going to be a relatively easy event to warn for. You just slap on severe thunderstorm warnings till it's through our forecast area. Very quickly, we learned that it was not going to be that easy, and all of a sudden, tornado warnings were flying out the window. So being able to anticipate this kind of change is really important to be able to message the threats with a high-end severe weather event to the public and our partners, especially in an event that's difficult to forecast to begin with. So that's why we're going to talk a little bit about some of the subtle signs and clues in radar and satellite data that the system was evolving and how that relates to impacts. So what we're going to do is we're going to start by looking at some radar data followed by some satellite data here, just looking at the structure of the derecho. On the left-hand side, that's data from the Quad Cities radar. The right-hand side is data from the Chicago radar. Roughly 1 hour, 30 minutes to 1 hour of data. They had different scanning strategies, so I had to make do with what I could to make the loops have the same amount of images here. But what's remarkable is if I didn't tell you that these images are roughly 2 hours apart, I think it would be easy to make the incorrect assumption that these are two completely different systems that occurred on two completely different days. So it's remarkable that the system underwent a really dramatic change in structure just across Illinois. And you'll notice that I actually kept the scale of Illinois in the blue contouring here the same. So you can really see the change in the size of the storm. When it was going across Iowa, it was a compact bow echo, a Boeing mesoscale convective system. It had a real obvious circulation on the northern side. We sometimes call that a bookend vortex, mesoscale convective vortex, or MCV for short. And you had merging storms that were emerging into the northern side of that bow there. And actually, many of those were supercells that produced damaging hail and even a few tornadoes themselves. If you compare that to the radar imagery on the right-hand side across northeastern Illinois, looks completely different. You had a much longer bow shape, if you will, a much longer elongated north to south section that was more linear. You can actually see some embedded line echo wave patterns, some curly cues in there. You still had the compact circulation, perhaps it's more obvious now along the Wisconsin-Illinois border. And you could also see just a different character in the radar echoes across central Illinois there, where you have signs of a surging cold pool. So two completely different structures, just 2 hours apart. And I will also mention, you see some of those high reflectivity splats just west of the RDA there in Illinois. That's actually quarter to ping pong ball size hail falling out of this system. Pretty unusual for a squall line to produce hail that large. And maybe it gives some signals that we're dealing with kind of a different structure entirely. I do want to throw on some satellite data here since we're in a satellite book club. This is just the channel 2, the visible satellite imagery here. And it still looks quite different from the left-hand side to the right-hand side. Obviously, we're dealing with an intense system in Iowa. You can see the overshooting tops and the gravity waves emanating from those convective towers. But if you compare that to the imagery on the right, it looks very different. You have, I would argue, much more intense convective towers. You have overshooting tops that are poking even further into the tropopause. And again, it's along the entire leading edge of the system from southern Wisconsin to central Illinois. A lot of times we also like to look at what we call it the sandwich imagery. It's the IR and visible satellite on top of each other. This also helps us assess the strength of updrafts. And again, you can see there's a clear difference from the system in Iowa to Illinois, where most of the intense updrafts in Iowa were associated with that MCV, that vortex on the northern end of the line, versus across Illinois, the intense updrafts were ubiquitous from north to south. I do want to look at some base velocity data here, a different V, mainly because of how ridiculous the returns looked across Iowa. So this is the half-degree tilt. We're looking anywhere from 500 feet close to the radar to a few thousand feet at the furthest distance at the start of the loops here. And this rear inflow jet that was driving this bow echo across Illinois, or in Iowa rather, was just, it was ridiculous. We're talking about returns greater than 110 knots. You know, I've been living in the Great Lakes for most of my life, watching these mesoscale convective systems, and I can't think of any other convective system that had such a persistent and intense rear inflow jet as viewable from radar here, 110 knots. I would have loved to be a fly on the wall in the Quad Cities office to hear what they were thinking as this was coming toward them. Of course, I had my own problems in Chicago as this was coming through. On the right-hand side, it's a much less intense rear inflow jet. We're still talking about 60 to 80 knots. That's still obviously severe and producing damage, but it's not nearly as intense as the rear inflow jet presentation across Iowa. Now, if we were to zoom into northeastern Illinois here, and we're going to subtract the storm motion so we get the storm relative velocity, I'm going to add some circles here. We actually had pretty persistent circulations that were along the leading edge of this line. Some of them equally spaced, but just very persistent. They weren't, you know, brief and just a scan or two sometimes, like you see with some, you know, QLCS tornadoes. These were they're actually mesocyclones, embedded supercells embedded in this line, and that's partly why we had those hail splats. You had the stronger updrafts that were able to support larger hail. And if I were to track these circulations with time here, you actually see they match up pretty well with the swaths of fingers of damage that Scott had analyzed in that map. And it's not necessarily surprising. it's become pretty clear, at least in the literature and then with operational experience, a lot of times with squall lines where the rear inflow jet is maybe not as pronounced, the circulations are actually the most responsible for the damage, especially on the right-hand side of the circulations where you have the superposition of the rotational winds and any resemblance of the rear inflow jet. So what's really interesting here is we had a changing character of the system across Illinois. And to help explain that, I want to talk a little bit about squall line dynamics. This is an oversimplified view of how squall lines work, but I think it's still necessary and it helps explain what we were seeing here. A lot of times, operational meteorologists, we're looking at the interplay of the strength of a cold pool, that's the rain-cooled air, the natural air conditioning, and the ambient low-level shear that balances that cold pool. It's always kind of a battle balancing the cold pool and the low-level shear. And when it comes to the most dangerous squall lines, especially those that support tornadoes, we're especially concerned with balance sections. And what I mean by balance is that the cold pool is balanced by the low-level shear, and that promotes vertically erect updrafts. And the reason why that's important is because vertically erect updrafts are the strongest updrafts. You get more bang for your buck, you're less susceptible to entrainments. You also have greater precipitation efficiency, which in turn leads to stronger cold pools, stronger natural air conditioning, and stronger low-level convergence. And you get this self-feedback loop that ultimately leads to an intense portion of a squall line. And a bonus is you also get stronger low-level stretching, which is important when it comes to the potential for low-level rotation and tornadogenesis. Now, if you're to compare that with what we call cold pool dominant sections, this is where you have updrafts that are more rearward sloped, meaning they're sloped toward the rear of the system. They're sloped atop the cold pool. Relatively speaking here, they're comparatively weaker. You have comparatively weaker precipitation efficiency. This can still be a somewhat stable regime. Squall lines can survive for quite a long time in this kind of regime, but often they're not as intense as regimes that are more balanced with the low-level shear. And this can also signal the end stages of a squall line, especially if that cold pool or the outflow boundary gets too far ahead. I will say these types of regimes can still pack quite the punch, especially if that initial cold pool is really strong. But the potential for low-level circulations is certainly lower compared to those balanced regimes. And I know we're talking a little bit more about science here than some of us expected, but I think it's important to understand these different regimes in order to understand the different structure of this derecho. So I'm going to throw some annotations back onto the loop here just to show some of these different regimes that we can analyze based off of the reflectivity structure. And it's pretty clear that this balance section became a lot bigger. It became elongated across northeastern Illinois. And the reasons for that we're going to talk about in a little bit here. But what's also interesting is that cold pool dominant section where the cold pool or the outflow boundary is surging ahead was also pretty persistent across central Illinois there. So the next question we have here is, can we identify these different sections in satellite data? This is often an exercise that we like to try in our forecast offices. If we lose radar data, we obviously have neighboring offices have their own radars, but we rely on satellite data pretty often to help us make warning decisions. And we actually had to do this last year. Actually, not last year, it was this past summer. I can't believe it's still 2021. National Weather Service Milwaukee actually had gone down and lost their radar data, and we had to take over for them, and we had to issue warnings based on satellite data. So this is an exercise that we do pretty often to make sure we're proficient. So I think it's kind of a unique exercise to try here to see if we can identify these different structures just by looking at satellite data. So what we're going to do is we're going to look at just a couple of products here. First, we're going to be looking at just the visible satellite. Only going to be looking at about 30 minutes of data here. I'm going to be looping forward with my keyboard here so I have a little bit better access. And I'm just going to throw in some annotations here of some features that can help us identify these different sections of the squall line. The first thing I want to throw on here is the outflow boundary. And the way that we can identify that is just noting the little opaque white color there, the sharp edge. That's the cold pool advancing forward into central Illinois. The temperature difference between the cold pool and the ambient environment was like 20 to 25 degrees, pretty incredible. So obviously when that cold air mass is charging into the warm air mass, it's condensing immediately and you're getting the evidence of the outflow boundary surging ahead. You also can tell the difference in character in the updrafts. They're a lot more piecewise, if you will. And if I go forward here, you'll see that there. The updrafts are more piecewise, they're more jumpy along the outflow boundary there, and that helps us delineate the leading edge. I'm also going to throw on in the yellow contours here the intensifying updrafts. Again, you have those overshooting tops poking into the tropopause there, different character compared to across Iowa. And you can see the difference in the character from the outflow boundary to the intensifying updrafts, there's some uncertainty in where that transition point is located, because you have some of the cirrus that's starting to get ahead of the system there. But you can still reasonably outline these different sections pretty well. And what I want to do here is just for a sanity check is I'm going to throw on the radar data. This is looking at MRMS radar data. It kind of links together all the different RDAs into one composite image. And in the shading and the barbed fields, that's actually going to be the low-level shear, 0 to 2 kilometer shear in particular here, just so we can put all the pieces together and see where we have that interplay between the balance of the cold pool and the low-level shear. And I'll point out that the highest shear values there with the barbs, we're talking 30 knots, or those yellow shading images there. That's across northeastern Illinois, across the Chicago area. And that's where we would actually expect that balance to be more optimal to balance the cold pool. But I'll throw on the same annotations here, and you can see that what we were able to discover just in the visible satellite data was actually pretty good. If you look at the radar data, that transition point from the outflow dominant section to the balance section was still kind of tricky with satellite data, but just by looking at the visible satellite data, I think we did a reasonably good job right here in this exercise identifying the two different areas. So anyway, I can talk about this storm for probably hours here, and I don't want to talk your ears off, so I'm going to wrap it up here for the question and answer session. But just a summary, the damage across Iowa and western Illinois, it was largely driven by that rear inflow jet, 110 plus knots. You remember the 2 to 3 county wide swath of just really high end wind damage. Compared to northeastern Illinois, the damage was largely driven by those low level circulations, where there was that large balance zone that was supportive of those vertically erect and stronger updrafts. And satellite imagery actually depicted the different sections pretty well. Could easily identify that surging cold pool across central Illinois, as well as the intensifying updrafts across northern Illinois. And of course, having some understanding of the environment could help make those deductions as well. So with that, I will wrap up my presentation. I see it went on for about 19 minutes here, which is perfect. And I want to thank you all for your time, and I'll pass it back.
All right. Thank you for that, Brett. Very interesting talk. So now we encourage all our attendees to continue to stay on the line for our discussion, particularly those from our field forecast offices and regional headquarters. And Kashad and Lee will be posting a survey in the chat room. So if you have a few moments to check that out, if you have any feedback on this session or any of the other Satellite Book Club or their sessions, you can find that link in the chat room. And please join us next Thursday, December 9th at 11 a.m. Eastern. We'll have Pam Sullivan, the GOES-R program director, and she'll be discussing the GOES-T plans for launch and operations. And also, if you need any assistance with satellite products or questions just for the Satellite Book Club in general, you can feel free to contact the Tower S team with Lee Byerly and Kashad Bowman. And also more information will follow in an email from the Tower S team. So from here, we'll jump right into the discussion. I have a few questions that I see. So for Brett, can you go into a little more detail about how satellite data is typically used during severe weather operations and what products you're typically looking at?
Yeah, absolutely. Especially with the availability of the GOES-16 data, it's paramount in our operations. It's completely embedded with any severe weather. Actually, I would say any type of impactful weather, we're looking at it. But in particular with severe weather, the 1 minute imagery is really important to us, especially when it comes to like initial decision with warnings. We're looking at the 1 minute data like a hawk, trying to assess whether an updraft is still intensifying, because a lot of times you'll see features in 1 minute imagery well before you see it on radar. And I know in particular, some of us have actually used the 1 minute imagery decision making for tornado warnings to see if an updraft is intensifying for vortex stretching. So that's pretty important to us. But you know, the visible satellite and IR imagery is pretty important. Those are probably the most used channels for us. We also like some of the RGBs, the red, green, blue composites. They're like the for lightning potential, looking at whether you have glaciation in the cloud tops. That's pretty important for us as well, especially as we're supporting just countless outdoor events across the Chicago and Rockford areas. Being able to identify clouds that have a higher potential to produce lightning is important. But it also has an important use after an event as well, especially with this derecho. We actually use satellite data, especially sentinel data, to look for damage paths, especially to fine tune the start and end point of paths. Sometimes if you're looking with a magnifying glass, you can see evidence of little vortices everywhere. We're not looking for those. We're looking for clear damage paths that warrant additional investigation, and that's just become a huge part of our operations after an event as well. So I would say satellite data is just as important as radar data when it comes to severe weather. Like I said, we train on issuing warnings with just satellite data as well in case the radar goes down.
All right, to kind of follow up on that, how do some of these features diagnosed in satellite imagery, such as storm top characteristics, surging cold pools, like in these cases, how does that influence your operational decision making?
Yeah, I think a lot of it comes into just that first warning as a storm is first intensifying. I think a lot of operational meteorologists will admit the first warning is the hardest one. It's a lot of times the environment hasn't yet showed its hand. You're kind of like, is this going to go as planned, or is it maybe not going to happen? So satellite imagery is really helpful for us to anticipate whether a storm is going to continue intensifying, or if it is continuing intensifying, to help drop that initial polygon. But also, if it looks like a storm may be weakening on radar, a lot of times we'll be looking at satellite data. Is there a new updraft pulse? What does the environment look like upstream? Is there growing cumulus? Is there no cumulus? So there's obviously stability issues. It's absolutely paramount in our operations. It's equally important as radar data. And it's kind of interesting as a lot of times we actually train on real cases on a separate machine called the WES. And sometimes when you don't have GO16 data, you feel kind of uncomfortable because it's so important in our operations, so embedded into our operations.
Fantastic. Yeah, and there's a lot of comments in here. Outstanding presentation, great talk. One from Kevin Thiel is asking, for your WFO, did you find any value added using the 1 minute versus the 5 minute scenes with the ABI?
Yeah, I think we'll take the 1 minute data anytime we can get it. We know sometimes domains have to be prioritized based on impactful weather, but the 1 minute data is, I would say, definitely extremely helpful, especially with intensifying storms, but also identifying the potential for storms that produce lightning. Because sometimes when you have a rapidly intensifying storm, from the initial cumulus cloud to producing a lightning bolt can be 15 minutes. So the difference between 1 minute scans and 5 minute scans, you're looking at 14 or 15 scans versus 3. So yeah, we definitely have noticed a huge improvement in operations with the 1 minute imagery compared to the 5. Obviously, we'll take whatever we can get, but hopefully that answers your question there, Kevin.
Right, and then you had touched on that you can see some of these features on satellite prior to seeing them on radar too, so it seems like it does give some advantage.
Yeah, absolutely. Especially when a storm is like re-intensifying. It seems like a lot of times storms are weakening right when a warning is about to expire, and you have to make that decision: do we continue a warning downstream? And having the satellite data, especially the 1 minute imagery to show, let's say, another intensifying updraft pulse, helps us pull the trigger on a downstream warning all the time. We use that all the time.
Have you looked at other cases, such as maybe comparing this event with the May 8th, 2009 super derecho that moved through Missouri and Kentucky?
It's funny you mentioned that. We are actually looking at a few other cases. This one, the super derecho, that if, for those who aren't familiar, if I'm remembering the date correctly, that storm actually adopted like almost an eye-like feature, incredibly intense mesoscale convective vortex, and produced really high-end wind damage. I think it was like just south of St. Louis is where it was the worst. So we are actually looking at that event, as well as another one that was across the Sioux Falls forecast area that underwent a very similar evolution as this one. And although it's not explicitly related to satellite, we're trying to look at kind of the predictability of how these MCSs or mesoscale convective systems evolve. If there's sort of a common archetype going from, the initial burst of thunderstorms or supercells to a bow echo to kind of this elongated tornado producing monster, it seems like some of these systems undergo a similar evolution, and some of it may be tied to how a mesoscale convective vortex develops and the conditions that are favorable for that. So that is something we're looking at in earnest right now, and hoping to see if we can parse out some features that we can use operationally to anticipate these rapidly evolving structures. So short answer is yes, we're also looking at that St. Louis or Missouri case.
Yeah, there's some great questions in here. Another one is asking if you've employed the day-night band to analyze any power outages or that were observed during the city and town lights from this event.
Yeah, in this particular event, I'll say we did not utilize that explicitly. I know we saw a bunch of images like on social media across Iowa showing the stark difference. I probably should have thrown that in because I remember it was pretty dramatic. I'm going to say thankfully in a careful way here. We had the fingers of damage across our area that confined the worst damage to a more limited area. If we had that, what happened in Cedar Rapids, if we had that same thing happen over the Chicago area, I can't even imagine how bad it would have been. With how many people live here, talking about a metro of, millions of people impacted by those high end winds, and the power outages probably would have been far, far worse. But, it seems like the impacts across the Chicago area were more limited to those fingers. And because of that, the power outages were a little bit more limited as well. So again, I use that word thankful really carefully, but, I did see some of the imagery across Iowa showing the difference in power at night. And some of those power outages lasted weeks.
Wow.
So it just took a really long time for the crews to be able to clean up all the damage.
Yeah, you mentioned the fingers of damage. This one question is asking, do you typically find that the damage path characteristics resemble these cat claws? John goes on to say, I know some studies in the eye walls of hurricanes have shown similar characteristics, and this event was referred to as a land hurricane.
Yeah, there's a couple points I want to hit on in there. It seems like across the Chicago area, for whatever reason, if it's just the time of day that these systems hit us or whatever, it seems like we deal with these circulations more often than we would like to. Like I mentioned, our biggest tornado event was actually from another squall line that produced a cluster of tornadoes in these little fingers. You get these organized circulations that just are prolific with damage, whether it's tornadic or not. The damage is pretty much the same, just 100+ mile-an-hour winds. So we do see that actually a lot with these systems. And like I mentioned, we're starting to look at whether there's a common evolution where we can anticipate, hey, we're moving from this widespread, bag of wind to these little fingers. And if we can anticipate that better, then we can, effectively message that better and adjust our warning strategy. But I also want to hit on that analogy of the inland hurricane. I know that some people kind of balked at that, saying it's a completely different system. I'm actually going to say, no, maybe this was pretty similar to that. When we're talking about a mesoscale convective vortex, an MCV, the dynamics are actually pretty similar to the dynamics that generate hurricanes. You're talking about a massive amount of latent heat release. There's a lot of condensation that's occurring in the system that generates kind of a potential vorticity response. You get a little bit of spin response. And when you don't have a lot of shear, actually these circulations can persist for days. And that's not all too different from what happens in the tropics. A lot of times when we talk about tropical systems, we're talking about shear, right? Because shear disrupts those circulations. So I would argue that sometimes these convective systems have similar dynamics to tropical systems, where you have just a massive amount of latent heating that generates these circulations that can influence the evolution of the system entirely. I know it's a little bit controversial, may have rubbed some people the wrong way with that, but I think these are similar. So I actually really appreciate that comment that was made.
Did you use a lot of GLM data during your warning decision process during this event?
I would say during this event, admittedly not as much, partly because, well, for a couple of reasons. Number one, we knew this thing was severe no matter what. But in number two, when the thing was evolving to the threat of tornadoes, we were kind of having to adjust on the fly. It was kind of a coordinated chaos is what we like to say sometimes. But I will say we use GLM data very often in warning operations. There's a lot of literature out there that looks at lightning jumps or an increase in lightning as a sign of an intensifying updrafts. And I think anybody who's been out in the field if you want to say storm chasing or out looking at a storm in the plains, there's kind of like this idea that when you get all of a sudden you have cloud to ground lightning strikes left and right, hey, this updraft's intensifying, we need to pay attention to this. So yeah, that's definitely something that we also take into account, the GLM data and warning decisions. A big lightning drum can sometimes be kind of the straw that broke the camel's back to lead us into issuing a warning for sure.
Okay. Speaking of polar satellites, did you use any sounding data such as NewCaps? I know there was a NOAA 20 pass that went over the Chicago area around 1840Z. Ken says it would be interesting to see the vertical profile data, especially in this downstream environment from the Derecho.
That is a great question and a great point, and that's actually something behind the scenes we're trying to get our hands on. We didn't look at it in real time, I will admit, but one aspect of this event that I didn't really touch on here, just in sake of time, is the environment actually changed pretty rapidly ahead of this system. The low-level shear across Iowa was actually not that strong, but when it moved into Illinois, the low-level shear increased pretty rapidly. In fact, I'll just go back to a slide here. This little bullseye of 30 plus knots across the Chicago area developed really fast, and we did not anticipate that. And something that we're actually kind of curious is whether that was demonstrated in some of the the derived data from satellite data, the derived wind profiles, whether it captured that. Because we were able to see the kind of after the event, we looked back at some data like, why did this happen? And we saw actually in aircraft sounding data, it actually captured this increase in wind speed really well. And I don't think I mentioned it during the talk, the wind shear analyzed here is actually from the RAP, it's modeled wind shear, and the RAP actually kind of indicated an increase as well, which is interesting. But kind of a long answer to this question is, yeah, we want to look at the derived satellite data to see if that pinpointed the evolving environments. And again, that could give us clues to an evolving structure before it happens as well.
And it looks like just a follow-up comment from previous question. Scott says there are some notable cases of MCVs moving over the Gulf and becoming named storms, such as Barry, and I believe that was 2019.
Gotcha. Yeah, I think the dynamics are kind of similar here. I think the Storm Prediction Center will admit sometimes these MCVs are really tricky to forecast, and especially downstream impacts. A lot of times the most persistent ones actually develop in environments with not a lot of shear, and I think it's because they're able to maintain themselves and they can trigger convection in subsequent diurnal cycles. Some of our tricky events in our area are actually MCVs that come from the plains, from big severe weather in the plains, and all of a sudden the next day the MCVs in our area, and bada bing, bada boom, we have a tornado outbreak. I think the dynamics are kind of similar to what you may see in the tropics with limited shear. So it's kind of an interesting avenue there for further research.
Yeah, that would be interesting to compare. Then kind of switching gears here. Seems like some of the offices involved did a great job of being proactive, sending out briefings to partners that helped close some of the COVID testing sites for the day, and DSS that proved effective for National Airspace System, providing ground stops at Chicago O'Hare. But knowing what you know now, would you do anything differently in terms of the messaging, partnerships, or tools, perhaps WAFIS, that help save lives during this event?
Oh, that's a good question. I had mentioned before how we're starting to look at these convective systems a little more to see if we can anticipate these changes ahead of time. That is just such critical information that we could, adjust our staffing and warning strategies and then message that to the public as well. Because like I mentioned, we thought that this was just going to be a giant windbag across our area. We did not expect it to evolve into like a tornado producing monster, into those fingers of damage. So had we had 2020 hindsight, we would have been able to message that a little better, saying, hey, it's turning into fingers of damage, and be able to message that better. And you mentioned the aerospace there. I didn't talk about that at all in the presentation here, because that's a whole nother presentation in itself. This system was incredibly impactful to the aviation airspace across the country. I believe, Sharon, are you at the CWSU there? So you probably firsthand that, when you get a big line of storms, granted, maybe not so much in the southwestern United States, but a big line of storms, you can't fly through that. And a lot of times when you get a big, north to south band of storms, that's really problematic for airports and air traffic routes. And this particular event was extremely impactful. Our staff at our office, not to brag, but they did an incredible job identifying the potential for this. They kind of went all in with our midnight shift and the potential for this line of storms to make it through our area. And we had mentioned in our TAFs, like 18 hours before it happened, the potential for a line of gusty storms. Really risky, but in this case, it paid off. And because of that, at least the Chicago terminals, they're able to plan really effectively before it came in and led to ground stops. And actually, the CWSU in Aurora, which is northwest of our office, as well as Chicago O'Hare, they actually evacuated due to circulations. And one of the circulations went really close to Chicago O'Hare Airport. So it was, I think, just a great example of the partnership between WFOs and CWSUs and the FAA to plan for an incredibly impactful event, even if it has low predictability, and kind of going all in one scenario saying, hey, if this happens, it's going to be really bad. And in this case, for better or worse, it worked out in that way. So yeah, thanks for bringing up the aviation aspect. That's a huge element of this storm.
Yeah, definitely. I know it's one of the impacts that maybe people don't think about as much, but yeah, it seems like you have great relationships with CWSU, and I liked how you hinted on the collaboration between other offices. But
yeah, absolutely. Oh, go for it.
No, go ahead. Yeah.
Oh, I was going to mention, as this was coming across Iowa, our office, Chicago, as well as northern Indiana, we sort of had the best seats in the house because we just had to watch it coming toward us. I really feel for the folks, in Omaha, Des Moines, and Davenport, where they really were at ground zero, but also this came really fast at them. And they didn't necessarily have the benefit of watching it for hours coming toward them, but they were relaying to us, especially the Davenport office, relaying to us what was happening there. That the winds were lasting longer than 60 minutes, that they're having 100+ mile-an-hour wind gusts, and we were able to really adjust our staffing because of that, because we knew of what was coming, because of what they relayed to us. And we were chatting with northern Indiana about what was coming, and a whole nother aspect of the system that I never touched on is this also generated a meteo tsunami in Lake Michigan, a little tsunami. And we were actually able to identify that potential after talking with the Davenport office and some of the pressure jumps they were having across their area. We're able to get products out across Lake Michigan in anticipation of this meteo tsunami. And to my knowledge, I think this may have been one of the first forecasted meteo tsunamis that's happened in the Weather Service, and it occurred, and we had products out hours before it happened. So that was a collaboration with Quad City, Chicago, northern Indiana, and Grand Rapids, and just fantastic teamwork to identify a threat and get the word out fast.
Fantastic. Yeah, it looks like we still have maybe a few more questions in here, but starting to get into our time limit. So I'll go ahead and turn it over to Jordan. And if anyone has any other questions, feel free to post those in the chat and we'll try to get to them and answer them.
Okay, thank you so much, Sharon. And thank you so much, Brett, for your presentation. Really great and a really impactful event. Hopefully the audience enjoyed it. I know I did. As Sharon mentioned, next week, Thursday, December 9th at 11 a.m. Eastern Time, Pam Sullivan will be talking about GOES-T launch and operations. That will be an hour earlier than normal. So if you're a regular Satellite Book Club attendee, please make sure that you have your calendar adjusted. GOES-T launch currently scheduled for March 1st of 2022. So we're closing in on that date. Countdown has started. Also, if you have any questions related to the configuration of satellite products, the Tower S team is here to help you. Please reach out to John Evans, Lee Byerly, Kashad Bowman. If you have any questions about AWIPS or the Satellite Book Club, you can reach them there via email or in the NWS chat. So with that, thanks once again to our presenter and our facilitator, Brett and Sharon, for today. And thanks to all of you for being with us. Please stay well, and I hope you'll join us again next week. Thanks, everybody.